Welcome to Lesson 4C, the mechanical energy equation. In this lesson, we'll talk about the mechanical energy equation, and this will involve two new concepts, deformation work and viscous dissipation. First, a derivation. Before we derive this equation, I have a few comments. First, it is an equation for the kinetic energy of the fluid. It is derived from mass and linear momentum equations, so therefore it does not come from the first law of thermodynamics. I'll call this the real energy equation. We'll deal with this one later. Because it's not the real energy equation, it is unnecessary in terms of our basic fluids problem with 6 equations and 6 unknowns. I don't mean to be rude, but your very nature is rude, bro. Talk about rude. You're the rude one. Just let me ask my question. Sir, if it ain't necessary, why are we even discussing it? That's a good question. Why should we discuss it then? Well, it aids in physical understanding. It will be extremely useful later when we discuss turbulence, and it will be combined with the real energy equation to simplify and understand some of the terms. Now let's derive it. We start with Cauchy's equation, which we had derived in a previous lesson. Remember that this is the general linear momentum equation for any fluid. Now let's multiply by ui. Note that this is a vector equation. In tensor notation, multiplying by another vector with subscript I implies a dot product of vector ui, the velocity vector, and Cauchy's equation. We get rho ui dui dt equal rho ui gi plus ui del tij del xj. Notice how in tensor notation, all we did was multiply each term by ui, and it's automatically a dot product because now the I is repeated and summed. Let's manipulate this term by using the reverse product rule. We write this as d dt of 1/2 ui. These two circled terms are equivalent. If you don't believe me, do the product rule on this, and you'll find that it leads to this. Thus we can write the above equation as this form, which we'll call the mechanical energy equation, and this is in non-conservative form. Again, for this term on the left, when you expand ddt, you will have velocities as coefficients of some of the derivative terms. Now we can apply continuity and expand the material derivative term and do a bunch of algebra to write this equation in conservative form. This now has 4 terms. The 2 terms on the right are the same as previously, but we've manipulated the left-hand side into these 2 terms. This is our mechanical energy equation in conservative form. To refresh your memory from a previous lesson, we had used psi as some general property, where psi is the conserved property per unit mass. And this first term, for our general case, was del t rho psi. So here, psi equal 1/2 ui, which is the kinetic energy per unit mass. Capital psi is mass times psi, or mass times 1/2 ui here, and capital psi is the conserved property, which here is the kinetic energy itself. Note that the left-hand side of this equation is thus the total rate of change of kinetic energy per unit volume following a fluid element, and these terms on the right-hand side are sources or sinks contributing to the change of kinetic energy per unit volume. We define psi and capital psi. Note also that rho times psi is the conserved property per unit volume, which is rho times 1/2 ui in our equation, which are the terms we see in here, rho psi. I summarize these 2 forms of the mechanical energy equation here, the non-conservative form and the conservative form, and I typed out these definitions of our quantities that we discussed up here. Again, the left-hand side is the total rate of change of kinetic energy per unit volume, and these 2 terms are sources. This term is the source of kinetic energy per unit volume due to gravity. But what is this term? We'll have to look into that one in more detail by discussing something called deformation work. Going back to a previous lesson, we consider a material volume of fluid, which I call a potato here, with some triangular surface element dA. This is vector dA. This is the control volume, and this is the material volume, which happen to be at the same place. They're coincident at this time t. we also have some element of force, dFs, in some direction acting on this surface element dA. The rate of work is this vector dFs dotted with u, or dFs sub I ui in tensor notation. How do I know this? Well, work is a force dotted with a distance. You have to have both a force and a movement to get work. So the rate of work is force dot distance over time, but this is velocity. So the rate of work is force dotted with velocity. The velocity vector of this little fluid element can be in some direction different than dA and different than dFs. The rate of work on this little element is then dFs I ui, or the dot product of the force and the velocity acting on this little triangular element. If you look back at lesson 3D, I copied and pasted a portion of that lesson here, where I draw 3 projections of surface element dA that are aligned with the coordinate system. dA1, dA2, and dA3 are the components of vector dA. So let's examine this term by using this diagram. We write dFSI ui is the rate of work done by surface stresses on our surface element. Well, if you look back at lesson 3D, we split this dFSI into 3 components by multiplying each component of the stress tensor with the corresponding surface area acting in the x1 direction, with similar expressions in the 2 and 3 directions, which we group together in tensor notation as dFSI equal tji daj. Notice that this is a vector, but we want dFSI times ui, the dot product. Therefore, dFSI ui is equal to tji ui daj, which is a scalar. I should mention here that the mechanical energy equation itself is a scalar equation. Now we can say that the total rate of work done by surface stresses is equal to the integral over the whole area of this expression, tji ui daj. Now we use our friend Gauss's theorem to rewrite this as a volume integral of del xj tji ui d volume. These are the same, and what we're doing is talking about a tiny element of volume, dv, within our volume v, or our potato. Either of these blue circled terms is the total rate of work done by surface stresses, but we now express it as a volume integral. So this integrand represents the total rate of work per unit volume done by surface stresses. I summarize that here. The total rate of work per unit volume by surface stresses on a fluid element is simply this integrand del xj tji ui. But since tij is symmetric, we can write it as del xj of tij ui. I point out that you can derive this equation also, or alternatively, by looking at a small fluid element and doing truncated Taylor series expansions around all these surfaces, as we've done previously. Now let's do some algebraic manipulation, namely by the product rule. This term is equal to tij del ui del xj plus ui del tij del xj. The 2 circled blue terms are the same. I'll write this out because we'll need this later, and I'll call this equation 2. Let's just examine these terms. As I've said, this first term is the total rate of work per unit volume done by surface forces on a fluid element. This last term is the rate of work per unit volume contributing to an increase or decrease, this can be either a source or a sink, of kinetic energy of the fluid element. In other words, it accelerates or decelerates the fluid particle. But what about this middle term? We've split this total work term into 2 parts, one that contributes to the increase or decrease of kinetic energy, and this one which does not. What does it do then? Well, we have forces and velocities, so work is being done by this term, but it does not change the kinetic energy. Instead, what it does is it deforms the fluid particle without accelerating it. Therefore, we call this term tij del ui del xj the deformation work term. And being consistent with our descriptions here, it's the rate of work per unit volume causing deformation of the fluid element. Physically, this term does not affect kinetic energy, but it does affect internal energy of the fluid element. This is an important concept. Now let's consider this stress tensor Tij. For a Newtonian fluid, recall that Tij was negative P delta Ij, where P is the pressure, plus tau Ij, which is the deviatoric stress tensor. Therefore, Tij del Ui del Xj is negative P del Ui del Xj delta Ij plus tau Ij del Ui del Xj. Or, contracting that middle term, we write it as negative P del Uj del Xj. Let's label these terms. We called this the deformation work term. This middle term represents heating or cooling of the fluid element by compression or expansion. And this last term we call viscous dissipation. We'll give it the symbol lowercase phi. Technically, it's a rate of viscous dissipation of kinetic energy per unit volume, but most people call it viscous dissipation by itself. Phi represents an increase in internal energy due to friction. Note that this middle term can be positive or negative. It's reversible. It deals with a reversible process, and it's 0 for the incompressible case, since del Uj del Xj is 0 for incompressible flow. But this term is always positive. It's due to irreversible processes, and it's not 0 for the incompressible case. We summarize that phi is the rate of viscous dissipation, and it's defined as tau Ij del Ui del Xj. Keep in mind that this is due to irreversibilities, namely friction. So let's write this equation with this term now called phi as shown here, and recall equation 2 with the terms rearranged, which is this equation, but let's plug the above into this equation, and let's call this equation 3. Finally, let's plug 3 into equation 1, which was our mechanical energy equation in conservative form. So finally we get del T of 1/2 rho Ui plus del Xj of Uj 1/2 rho Ui equal rho Ui Gi plus del Xj of Tij Ui plus P del Uj del Xj minus phi. This we will call an alternate conservative form of the mechanical energy equation. This is the form that will be very useful to us, especially when we get into the study of turbulence. Thank you for watching this video. Please subscribe to my YouTube channel for more videos. 1, 2, 3. That's all there is to it.